Testing. Okay, good evening. So this is where we stopped last time. Before that, I have asked the TA to post the first assignment 1, so in this week. So you will probably get it in a day or two. You will be given 2 weeks time to finish it. Okay, so should be. It's not a lot of. It's I think just take you at most 1 or 2 hours. That sort of order. Okay. Okay, so this is where we stopped last time. So we were talking about, okay, so for so how should I? No. Anyway. So we're talking about how to coordinate the transmission in a multi-user setup so that the receiver will have an easier task to demodulate the signals, the data from each one of you, right? And we talk about FDMA and TDMA. FDMA is trying to partition the resource in the frequency domain. So given a certain spectrum, you try to partition into many frequency slots. And then you go and assign each user to transmit on a particular frequency channels. Okay, so we can imagine or visualize. You can transmit your data simultaneously on your assigned frequency channel, and because you're transmitting on different frequency channels, there won't be any interference. So if I want to receive the signal from any one of you, I just need to tune to the correct channel, and I will be able to decode your signals, right? On the other hand, TDMA is trying to partition the resource on the time axis. So, so the time dimension is partitioned into many time slots. And then each one of you will be assigned a different time slots. So when you transmit, when you transmit on your time slot, you can transmit with the entire spectrum. You can use the entire spectrum. But then you cannot use the entire spectrum at all times, right? So when your time slot expires, you need to finish your transmission and then let the other use the spectrum. So in other words, in TDMA, it's like each one of you takes turns to share the spectrum. It's a time-sharing arrangement. So each of these basically would be able to accommodate multi-user transmissions. Now, of course, I also mentioned about CDMA. And for CDMA, things are slightly different. So if we operate in CDMA, so each one of you will so signals from each one of you are not separated by time. They are not separated by frequency. So your transmission happens simultaneously. But we are separated. You guys are separated by having something different codes. So the analogy I used was you are using different languages. Okay. So, but I will explain this in more detail later. Now, so as I said, right, with frequency division multiplexers, the allocated spectrum to an operator is divided into n frequency slots, and each channel or each user will have a bandwidth of W over n. And different mobiles are assigned to transmit at different frequency slots, so there won't be any interference between simultaneous transmissions. Okay, and this is called orthogonal channels. Now the implication of orthogonal channels or non-orthogonal channels, we'll discuss this later on. There are some system level implication based on this orthogonal partitioning versus non-orthogonal partitioning. TDMA, again, you end up having orthogonal channels, okay? So the question we want to explore is, okay, so which one is more effective? More effective means which way of partitioning the resource will end up having more users or more channels available to the users. So how do we formalize this comparison? Okay, so let's do a toy example. So let's say we have a 15 megahertz of frequency spectrum. So you pay a lot and you get the 15 megahertz of spectrum. This is the license bandwidth. Okay, so you get 15 megahertz of bandwidth, but this is too big to assign to individual users. Okay, so you need some partitioning scheme to partition into channels so that you assign each channel to a user. Now, for fair comparison, we are comparing 2 ways of partitioning the resource, right? FDMA or TDMA, which way will result in more channels. But for fair comparison, we got to have some requirements quality of service requirements on the channel. So the constraint is, let's say we want the bit rate per user is 25 kilobit per second. And then we are using binary modulation. Okay, so let's say these are the constraints. So under this constraint, we try 2 ways of partitioning this 50 megahertz of spectrum and try to see which way we end up having more channels. More channels means more capacity. Okay, that means we can accommodate more users. Okay, so let's try the FDMA. Now with FDMA, that means the resource dimension is on the frequency dimension, right? So this is the frequency. This is the 15 megahertz of spectrum, right? So suppose, so the number of channels we can have using FDMA is simply given by the total spectrum bandwidth I have, 50 megahertz, divided by the transmission bandwidth per user, right, per channel. That gives you the number of channels that we can partition from FDMA, right? So the question is, how much bandwidth is needed per user? So, and remember, each user needs to enjoy this quality of service, right? So the bit rate per user needs to be of this level. And we constrain ourselves to be using binary modulation. So remember, bandwidth is equal to 1 over Ts, right? Ts is a simple duration, as we talked about in the first part. So, and also bit rate is log 2m times 1 over Ts, right? Bits per second. In this case, we are using binary modulation, so this factor becomes 1, right? So, and therefore, and we need this to be what? To be 25 kilobit per second. This is the requirement per user, okay? So from this, we know the bandwidth per user needs to be 25 kilohertz as well. Is that okay? With binary modulation, bit rate equals to bandwidth. Okay? So now each user, each channel, each frequency slot we have require a bandwidth of 25 kilohertz. So altogether, how many frequency slots can we partition? It's very simple math, right? So substitute back to here. So the number of frequency slots we can partition using FDMA is 15 megahertz divided by 25 kilohertz, right? So if you do the math, this is 600. So we can partition into 600 frequency channels in this toy example using FDMA, so that each user will be able to enjoy a bit rate of 25 kilobit per second. Is that okay? Now, this is not the only way to partition the resource, right? The second way to partition the resource is using TDMA. Now, using TDMA, what do we mean? Using TDMA, that means we are partitioning the resource on the time axis. So in this case, let's consider a reference user who is assigned with time slot 1, okay? So if we look at the transmission bit rate of the reference user, so this is the first time slot. Let's say the time slot duration is tau. And then this first time slot repeats itself once the frame duration is TF. Okay, so these are the timing parameters for the TDMA. So this is 1 frame, and this is 1 time slot. So this is the time slot assigned to the reference user number 1. So that means this user can only transmit on the time slot 1 and shut up on the other time slot, right? So, and this is the bit rate. So we are trying to, let's take a closer look on this diagram. So the number of time slots that can be partitioned using TDMA is simply given by the time resource, right? So this is the time we have for 1 frame divided by the time slot duration, tau. So this ratio gives me the total number of time slots I can partition out of a frame, right? Agree? Okay. Now the thing is, when this reference user transmit, nobody is going to share the spectrum. So this guy, reference user 1, can use the entire spectrum. The entire spectrum is 15 megahertz, right? So what is the bit rate here for reference user number 1? Under the same constraint, binary modulation, right? Bit rate equals to bandwidth, right? So if I have a bandwidth of 50 megahertz, that means during this time slot transmission, this guy is transmitting 15 megabit per second here, right? But unfortunately, this user 1 cannot sustain this bit rate forever. It can only transmit at this bit rate during this assigned time slot. Is that okay? Now for the other time slot is 0. Now, but there is a quality of service constraint. The constraint is the average bit rate per user needs to be 25 kilobit per second, right? So what is the average bit rate? From the basic definition, bit rate, what is the bit rate? The number of bits delivered over one frame, let's say. The number of bits delivered divided by the time duration of a frame, right? So the numerator is the number of bits transmitted per frame divided by the time of a frame. That's the bit rate, right? So what's the numerator? Total number of bits delivered per frame, right? So if you look at this picture, what is the total number of bits delivered in one frame? This area, right? This area gives you the total number of bits delivered in one frame. So what is this area? 15 megabit per second times tau, right? And the denominator is the frame duration. And this needs to be what? This needs to be 25 kilobits per second, right? From the constraint. So that means what? From this equation, that means this ratio is the inverse of this ratio, right? So that means this ratio, frame duration divided by time slot duration, is equal to 15 megabits per second divided by 25 kilobits per second, which is 600 as well. Can you see that? Okay, so this comparison seems to draw a conclusion that both ways, FDMA and TDMA, are equally good. They give you the same number of, they can support the same number of users under this quality of service requirement, right? And we shouldn't be surprised by this fact. They are equally effective because FDMA is trying to partition on the frequency axis. TDMA is trying to partition on the time axis. These are two independent resource axes. So there's no reason why one is better than the others, right? Theoretically. So they should be equivalent. So this should be the expected outcome. Is that okay? Now, however, if you look at the generation of mobile cell phone systems, the first generation, the so-called 1G system, is based on FDMA technology. The 2G system, like GSM, whatever, is based on TDMA technology. So it seems like as you go in a higher generation, you must have more advanced technology, right? So the fact that 1G is based on FDMA and 2G is based on TDMA seems to suggest that TDMA would be superior than FDMA in some sense, right? So what is the, why TDMA becomes the basis for this 2G system, not FDMA? Now, so we have to talk about, so we found that actually we have to take in, theoretically speaking, they are equally effective, but there are different implementation constraints. Now for FDMA, now using this whole example, if I need to fully equip my base station to support these 600 users, then the base station needs to equip with what? Equip with 600 pairs of radios, right? So if I want to talk to these 600 guys simultaneously, I need to have 600 radios. So we know radios are basically built, especially high-power radios, that include high-power filter, high-power power amplifier. These kind of analog components, they cannot be, they are actually pretty bulky, and they burn a lot of power, okay? So if your base station has to equip 600 of these kind of radio, bulky radios, your base station will be super big, and you will burn a lot of power, generate lots of heat. That in turn require lots of air conditioning loading, okay? So everything scale up. So that's bad, right? Because in this case, you end up having very bulky and power-hungry base stations. Now, on the other hand, what about TDMA? If you partition the resource using TDMA, if I'm a base station operating using TDMA, if I want to talk to 600 users operating on 600 time slot, how many radios do I need? I just need one radio, right? I just need one radio. I just need one radio and time share this radio with 600 users. So in that sense, TDMA base station will be less bulky and generate less heat, which is implementation-wise more friendly, right? So that's the advantage of TDMA. However, if you look at the FDMA again, when a user transmits on the frequency slot, so that user will transmit forever, right? So it's continuous transmission. Now, the bandwidth of the signal transmitted for a user is 25 kilohertz, right? So, and as we talk about that for these kind of applications, let's say for outdoor propagation, the coherence bandwidth is of the order of 100 kilohertz, right? For outdoor. So if you do the math, for this FDMA situation, do you need to worry about frequency selective fading channel? Do you need to worry about the ISI problem we talked about last time? No, right? Because the transmission bandwidth is much less than the coherence bandwidth. So you are talking about flat fading problem only. Okay? So for FDMA, every user, you just need to worry about flat fading channel, which is a one-star problem. In other words, you don't need to worry about equalization, okay? Which is good. What about TDMA? When the reference, when you transmit on one time slot for the reference user, what would be the bandwidth needed? What's the transmission bandwidth like? The transmission bandwidth is the entire spectrum, 50 megahertz, right? In this case, the transmission bandwidth is much larger than the coherence bandwidth. The coherence bandwidth is only around 100 kilohertz, okay? So you are talking about, if you do the math, you're talking about 150 echoes, right? When you say a letter A, you have 150 echoes following on. So then you are going to hit this frequency selective fading channel, right? So you have this irreducible error floor. And since you're talking about 150 echoes, the irreducible error floor would be pretty severe, right? So that means you have to worry about equalization. And as we talk about, brute force equalization is very difficult to do. If you dump all the burden, equalization burden to the receiver, the complexity just becomes exponential. So there's no good solution for that. So that's the problem of TDMA, right? So you see that if you compare this implementation consideration of FDMA and TDMA, it's not like one is always better than the others. FDMA has an advantage, no need for equalization, but it has a disadvantage, very bulky base stations. But TDMA has an advantage, only one radio would do the job. But it also has disadvantage, right? Compressed equalization. So in this situation, these two technologies are called complementary. So they cover up each other. So in practice, 2G systems, in fact, takes a hybrid approach. It's a hybrid between FDMA and TDMA. They do not partition the resource directly using TDMA because otherwise you have very compressed equalization problem. So instead, what they do is they first partition using FDMA into something called carrier. Each carrier has a bandwidth of 200 kilohertz. Bandwidth, okay? But 200 kilohertz bandwidth carrier is still too big to assign to a user. And then for each carrier, they further partition using TDMA. Into 8 time slot. And then they assign a time slot to a user, okay? So if you count the total number, so with 15 megahertz of spectrum, you partition into 200 kilohertz carrier, how many carriers do you have? How many radios do you need for the FDMA to fully equip? So the number of radios would be 15 megahertz divided by 200 kilohertz, right? This is the 75. So instead of 600 radios, a fully equipped base station just requires 75 radios. Is that okay? Now, and then for each carrier, you partition using TDMA into 8 time slots, right? So you have 8 time slots per carrier. So the total number of channels is still 600. 8 times 75, 600. Okay? So it's the same total number of channels. It's just the way you partition into channel, go through these 2 steps. Now, what about the problem of equalization? Now, in 1 time slot, if you partition it this way, when user transmit on, let's say, the first time slot, what would be the transmission bandwidth? Previously, if you partition directly using TDMA, the transmission bandwidth per time slot would be 50 megahertz, right? But now, what is the bandwidth? Bandwidth is 200 kilohertz only, right? Because you're partitioning from a carrier. So the transmission bandwidth for each user on a time slot is 200 kilohertz instead of 50 megahertz. So 200 kilohertz, you transmit on outdoor propagation. You still have to worry about equalization because the number of resolvable paths, resolvable symbols, is your transmission bandwidth, 200 kilohertz, divided by the coherence bandwidth, which is around 100 kilohertz. So this is around 2. So you have a frequency selective fading channel problem. But the number of echoes is just very limited, right? It's just like when you say a letter A, you receive 2 copies of your voices, right? So therefore, just brute force equalization will be able to do the job because you are not talking about a huge number of echoes. You're just talking about 2 echoes. So indeed, this is the scheme adopted by GSM. So every GSM mobile has an equalizer. And the equalizer is to deal with this with limited number of echoes. The complexity of the equalizer is reasonable because you are not talking about a huge number of echoes. Is that okay? So this is achievable by this kind of hybrid partitioning. So you can see this hybrid partitioning is to achieve the trade-off between the number of radios needed at the base station and the equalization complexity. Okay, so this is right. So this is what we talk about here. So this is the hybrid partitioning scheme. The total spectrum is first partitioned into some carriers, and then each carrier is further partitioned using TDMA into time slots. So this hybrid partitioning also have a modular design, meaning that when you set up the base station initially, you don't need to equip 75 radios. You can actually have a few radios, right? A certain number of carriers, and then you gradually upgrade your base station by installing more radios as the capacity demand increases. Okay. So when I talk about the term dimensioning, so if you work for operator in a network design department, so one of the job is to figure out what is the coverage, is there any coverage holes, right? What kind of power amplifier would be needed? That's the coverage perspective. But there is another dimension, it's called capacity dimensioning. So you need to look at the traffic demand and then determine how many radios, how many channels do you need to equip on every base station as well. Okay, so that whole thing is called dimensioning. All right, so any questions? So that's for TDMA and FDMA. In both cases, theoretical capacity is the same in both ways, and but they have different implementation challenges. Okay, and both way of partitioning the channels end up having orthogonal channels, meaning that signals from user 1 will not interfere with signals from user 2. And this orthogonal partitioning have an important implication on the network operator. I will talk about this later. All right. Now, then let's spend some time to talk about the third way of multi-user or multi-access scheme, so-called co-duration multiple access. Now, this CDMA is pretty interesting in the sense that it's unconventional. Unconventional in several senses. First of all, You can see from this picture that signals from different users, they are not separated by different frequencies. They are not separated by different time as well. So they overlap in time, they overlap in the frequency. And they are separated by having different codes. Okay, so I'll explain what do we mean by coding. And the fundamental technology behind CDMA is called spread spectrum. So let's look at the operation involved. So in this example, so the modulation data, modulation symbols, let's say you do binary modulation in the same traditional way. So if you were not to do spread spectrum or CDMA, you would just transmit the modulation symbol directly onto the air, right? Radiate out to the base station. But now with spread spectrum, you do one additional step. This additional step is called spreading. So let's explain, using a time domain picture, what is called spreading. What is the processing involved in the so-called spreading? Okay, so let's look at this picture. Now this is the complete modulation symbol. Okay, this is one symbol, second symbol. We consider binary modulation as an example. So one modulation symbol, second modulation symbol, third modulation symbol. So this signal would be like somewhere here. So if you were not to do spreading, you would just transmit this modulation symbol in the same way as we talked about in the earlier parts. Okay? But now, instead of sending this beautiful modulation symbol to the channel, you do one additional step. That additional step is called spreading. So what do we mean by spreading? Spreading is like this. So mathematically, let's say this information signal is called ST. So this is the modulated symbols. So instead of transmitting this guy, what you actually transmit is this guy multiplied by, this is called a spreading sequence, which is a sequence of +1 and -1. It can only take two values, either +1 or -1. So, and this spreading sequence, or so-called spreading code, is the so-called code. Okay? So mathematically, you just multiply the symbol, modulated symbol, with this random sequence of +1 and -1. So in this example, a modulation symbol is multiplied into this sequence. The sequence is +1, -1, -1, -1, +1, -1, -1, -1, +1. Okay? So different user will be assigned with different spreading sequence. Okay? But let's focus on one user, the operation. So by spreading, mathematically, we mean multiplying. But conceptually, you can think of this multiplication as like you use a knife. You chop a symbol. You chop this original beautiful symbol into many broken pieces. So after chopping this symbol into broken pieces, each of these pieces is called a chip. So what you transmit are these broken pieces instead of the entire modulation symbol. You chop this into many, many fragmented pieces. Okay? For some reason, we will explain. But this is the operation. So after spreading, in time domain, what you transmit are these broken pieces. Is that okay? So you chop one symbol into, in this case, 1, 2, 3, 4, 5, 6, 7, 8. You chop this into 8 pieces. Okay? Now there is one important parameter in this spreading process. This parameter is called spreading factor. So spreading factor is, suppose you chop one symbol into 8 pieces, then the spreading factor is called 8. Okay? So it's a symbol duration divided by the chip duration. This is called spreading factor. So this is an important parameter in the spectrum design. So for example, if you have a spreading factor of 64, that means you will take a modulation symbol, chop this into 64 pieces, and you transmit this 64 broken pieces per symbol. Okay? So these will be the broken pieces that you actually transmit into the channel. So that corresponds to this output. So this box is doing the spreading, or chopping the symbol into broken pieces. At the input of this box is the complete modulation symbol. At the output of this box is the broken pieces. Is that okay? Conceptually. So this is like a blending machine or whatever, a scrambler. Okay? So the input to this are just beautiful symbol, a complete symbol. Output to this are just broken pieces, smashed into pieces. Okay. So this is the time domain picture. It's a very simple operation. Okay. The corresponding frequency domain picture is like this. So this is the input signal to the spreading box, right? So before spreading, if you look at the frequency spectrum, the spectrum is something like this, the yellow spectrum. The bandwidth, this bandwidth is 1 over Ts, 1 over Ts, right? And this is a symbol duration Ts, which is pretty big, so therefore 1 over Ts is pretty small. It's a narrow band signal. But if you look at the spectrum after spreading, so the signaling unit, the time duration of one broken pieces is chip duration, right? So the bandwidth becomes 1 over Tc. So this becomes the bandwidth, the gray part. So in my example, if you chop a symbol into 64 pieces, the bandwidth becomes 64 times larger. Okay? So what you transmit, the spectrum becomes 64 times larger bandwidth, just like this gray spectrum. Now there is one additional constraint. Because this is only takes +1 or -1, so you can easily see that the energy of the transmitted signal is the same as the energy of the modulation symbol before spreading. Why is that? Because this is the definition of the energy, xt squared, time domain energy, right? So you substitute xt into here, so this becomes s squared c squared t dt, right? C squared t will be always 1. So that becomes, right? So that is the energy of the original signal before spreading. So the energy is the same. Because of this, remember the power spectral density. This is the power spectral density. Area of the power spectral density gives you power, right? So since they have equal power, so if you expand the bandwidth by 64 times, this peak level also needs to be reduced by 64 times so that the area remains to be the same. Okay? So that's why the spectrum of the output of the spreading process, the spectrum will look something like this. It's like you stretch on the base 64 times, but the peak is also suppressed by 64 times. Okay? So that would be the frequency domain picture before spreading and after spreading. Okay? Now, so what I have explained is just the process. Okay, I didn't explain why. I'll talk about why later. So this is what happened at the transmitter. Now let's look at the receiver. At the receiver, what do you do? The receiver has to do something reverse, so-called despreading. Now, at the receiver, so-called despreading, just to reverse the process. Now, if this is an intended receiver, that means you are a legitimate receiver. So this design, later on you will see that this design is not trying to guarantee any receiver can receive the signal. Okay, only legitimate receiver can recover the information. So if you are the intended receiver, you need to have two knowledge before you can despread, successful despreading. The first knowledge is you need to know the code. At the transmitter, you need to know the code that the transmitter used to chop the symbol into 64 pieces. You need to know the code. Okay? That means you need to know the knife. If you think of that as a knife, you need to know the knife that the transmitter used. Second, you need to know the timing. Know the despreading timing. I'll explain what do we mean by this. Now you must know these two things before you can have successful despreading. Now despreading process, suppose you know about these two things. The despreading process is very simple. Let's ignore the channel noise. Let's say at the input of the receiver, you receive these broken pieces. Okay? Suppose you know about these two things, then let's say yt is simply equal to the broken pieces. So now how do you recover the original modulation symbol? You do something very straightforward. This is the despreading output. You take this received broken pieces. You multiply with the spreading sequence one more time. Okay? And then you take the symbol average. Then this will give you This will give you, if you substitute this into the equation, so this is ST times CT, right? So you have ST times CT. That was the broken pieces that you received from the transmitter. And then you multiply with CT one more time. And then you take the average. So what do you get? This CT times CT becomes C squared T, right? So you have ST, C squared T. And then C squared T is always 1, right? So that becomes the ST. So mathematically, you can see the despreading process is very straightforward. You just need to multiply whatever broken pieces you receive with this spreading sequence one more time. Okay? Then you will regenerate the signal. In terms of time domain, this is just the opposite. So these are the broken pieces that you receive at the input of the receiver. So suppose you know the right code and you also know the right timing. Right timing means the first chip that you receive corresponds to the first chip of this despreading sequence. Okay? If the timing is aligned in this way, then you just multiply this again. +1 multiplied by +1 gives you +1. -1 multiplied by -1 gives you +1, etc. Then you will reconstruct the original modulation symbols. Okay? And once you recover this original modulation symbol, you can pass it to the standard demodulator and go through the demodulation data path. Okay? So this is the time domain picture of the despreading process. Now, as I said, in order for this to work, you need to know the spreading sequence. You need to know the knife, right? Now, suppose you don't know the knife. You try to despread with another spreading sequence. Let's say you try to despread with C prime T. C prime T. Okay? Now, then what happens? Is this will not be C squared T. This becomes CT times C prime T. And then you take the average. So CT and C prime T are two random sequences of +1 and -1. When you multiply them together, it's still a random sequence. So in this way, you will not recover the symbol. After this despreading operation with the wrong key, the output is still broken pieces, right? So that demonstrates the reason you need to know the right key. Now, suppose you know the right key, but you despread at the wrong timing. Then what happens? If you despread at the wrong timing, let's say you try to despread with a timing offset. Okay? So it's the right key but slightly offset. Then in this case, what you're doing is like this. So that becomes CT minus tau, and then take the average. Now, in this case, you won't be able to recover the symbol as well because the CT multiplied with a delayed version of itself is not guaranteed to be always 1, right? It still appears as broken pieces. So when you despread with the right key but wrong timing, the output is still broken pieces. You won't be able to recover the original symbol as well. Okay? So in order to successfully despread the broken pieces into complete modulation symbols, you need to know the right key and you need to know the right timing. Now keep this in mind. So of course, different systems will have different means of achieving this knowledge, which we will talk about this later. Okay? So this is a time domain picture of successful despreading. So you start from this receive broken pieces with successful despreading. Once again, you despread with the right key at the right timing. Okay? Right timing means the first chip that you receive in the broken pieces corresponds to the first chip of the despreading sequence. Okay? So if you know about these two things and then you despread, then the despreading will be successful and you recover the original modulation symbol like this. Okay? Any questions? In terms of the spectrum, this gray spectrum is the spectrum of your received broken pieces. After successful despreading, the spectrum becomes this yellow spectrum. Okay? So that's the frequency domain picture. Now the thing is, what we have talked about is the processing. Okay? What happens in the spreading process and what happens at the receiver, the so-called despreading process. But then the natural question you may ask is why? Why you want to do this? Now don't forget, in the spreading process, we don't see where is the benefit, but we see the cost. The transmission spectrum, the transmission bandwidth is now expanded by 64 times. If my spreading factor is 64, that means by engaging in spreading and despreading into my data path, I need to pay 64 times higher bandwidth cost. That's the cost I have to pay. Then what is the benefit? Right? The natural question you should ask is, okay, I pay 64 times higher cost. Then I should expect some kind of benefit, right? Some kind of reward. What is my reward? Do I get a higher bit rate? No, right? The bit rate is determined by the symbol duration, which is fixed already. The bit rate didn't change due to the spreading and despreading. I didn't get higher bit rate, so what for? So what is the motivation? Why we are doing this? Now, to explain why, we need to explain a little bit about the background of sparse spectrum. So sparse spectrum was not invented for this kind of CDMA operation. Instead, sparse spectrum was invented for military application. In fact, it's a very interesting story. So sparse spectrum was actually invented by a very talented lady. So that talented lady was reportedly having very high IQ, and then but she didn't. She was a movie star at that time, but then she has a very multi-talented. So while being a movie star, she was also very beautiful at the same time. And then being multi-talented, she is not satisfied with this, and then somehow in her spare time she also worked on this kind of communication problem, and then she invented this sparse spectrum scheme. So it's not that difficult. It's actually mathematically very simple, but very clever idea, as you will see. So the background of this invention is for military application. For military application, the primary concern is interference suppression. So why you have interference in military? Of course, right? So it's a battlefield situation. So two sides will. So on one side, you would like to use the radio communication on the battlefield, right? So that the whole army becomes an army. If there is no communication, the whole army becomes individual, right? It's not an army. So maintaining communication is very important. And of course, you want to do wireless communication, right? But then the other side, knowing about this, the importance of communication, they will try to destroy your communication. How do they destroy your communication? They may send some jamming signal to jam off your communication, right? So it's a usual situation in a battlefield or in a military context that you expect jamming, hostile jamming from your enemies. Okay, so sparse spectrum was invented to protect or suppress from these kind of hostile jamming. Okay, so you have this interference suppression. This is the primary advantage. That is to say, if your situation do not have interference, there is no point for you to use sparse spectrum. Okay? Sparse spectrum has nothing to do with, if you only have channel noise, if your system is just noise limited, then sparse spectrum will have no benefit for you. You pay extra bandwidth cost, but you have no reward. Okay? Then you should forget about sparse spectrum. So you should only think about sparse spectrum when you have interference problem. Okay? Keep this in mind. Now, of course, for military application, you also have another important function. So your enemy is always trying to intercept your communication, right? So how do they intercept? So they use a radio trying to scan the spectrum. So of course, they don't really know about your exact carrier for communication, right? Because that's usually a military secret. So what they do is they use a spectrum analyzer to scan the activity on the frequency spectrum, right? So if you have some kind of a signature like this, then they know this carrier frequency would be your communication channel, and then they can basically intercept your communication this way. Okay. So now the thing is, if you use the regular BPSK modulation, then the spectrum will be like the yellow spectrum, will be like this, right? So you will have a peak whenever you have this activity on a certain carriers on the spectrum. So then it can be easily intercepted. Now, however, the thing is, if you use sparse spectrum, let's say you chop a modulation symbol into 1,000 pieces, then that means the spectrum would look like the gray spectrum. That means the bandwidth you have to use will be expanded by 1,000 times, but the peak will also be reduced by 1,000 times. 1,000 times is 30 dB. So that means if you're using sparse spectrum, then your signature of communication will be something like this. Okay? So this is very difficult to recognize. compared to the noise floor. Because even if there is no activity, you will have some noise floor, right? So when you have activity, the spectrum would look very similar to the noise floor. So in this case, it is not that easy for your enemy to intercept your communication. So in a way, you try to hide yourself below the noise floor. That's another advantage of spectrum. Now, in terms of the commercial application, so CDMA system is the first commercial application. So CDMA, applying spectrum to communication, was pioneered by Qualcomm. You heard about Qualcomm, this company? So it was one of the very important companies these days. So it was a pioneer using spectrum for communication purpose. But the first attempt, which was not very successful, was using spectrum for satellite communication. That was in the 80s. But that turns out not very successful. So Qualcomm basically shuffled their business model and tried to use spectrum on mobile communication services. And that turns out to be very successful. So CDMA, later on in next chapter, we will talk about IS-95, which is the world's first CDMA standard. So IS-95 was pushed by, or basically invented by Qualcomm. Okay, so it was only adopted for commercial application, for communication purpose, only around 80s, and this was invented in the 50s. Okay. Now, of course, for commercial application, the probability of interception is irrelevant, right? So, interference suppression. So why do we have to worry about interference for commercial application? For cellular application, for example. Now, in the battlefield situation, of course, it's a different story. You have hostile jamming, right? But in cellular network, it is illegal to transmit without a license, right? So if I'm an operator, I set up some base station here and there. If my competitor sends some hostile jamming signal to jam off my base station, then that would be illegal, okay? And that is also criminal, so nobody will do this, okay? So if that's the case, then why do I have to worry about interference? Where are the sources of interference? Well, there are pretty much two sources of interference, even in a licensed spectrum situation. The first is something we'll talk about later on, is the multi-user interference. Okay? When the base station has to support the communication with multi-users, there will be multi-user interference. For example, in the CDMA setup, right? So the transmission from different users, they share the same spectrum and share same time, so they mutually will interfere with each other. This is called multi-user interference. Okay? So that's one source of interference, even in a licensed spectrum. The second source of interference is even if you are talking to just one user, as we talked about last week, you have multi-part problem, right? You have frequency selective fading channel. You may have echoes of your transmitter symbols, right? So you may have this inter-symbol interference. So that is another source of interference, ISI problems. So later on, you will see that because of this potential interference, that's the motivation for CDMA system to use spectrum technique. And primary purpose is to fight against this interference. Okay? And that's why even in commercial system, which is a licensed spectrum situation, you still have potential interference. These interference are generated by your own network, either by your own users or by the multi-part fading channels. Okay? Now let's try to understand why CDMA systems or spectrum can give you so-called interference suppression. And what do we mean by interference suppression? Let's try to understand this from a frequency domain picture first. Okay? Now, suppose this is a user, a reference user. So this is the modulation symbols, okay, before spreading. So if you look at the frequency spectrum, it's like a very sharp spectrum, like the yellow part, right? Okay. Now, after spreading, if you look at the output of the spreading, now there is a typo here. Suppose I chop a symbol into 64 pieces. I use 64 as an example because that's a parameter in IS-95, which we will talk about in the next chapter. So let's assume we chop a symbol into 64 pieces. Okay? If you look at the spectrum after spreading, so these are the broken pieces that you transmit. As we explained, the transmission bandwidth is now expanded by 64 times, right? But to keep the power to be the same before and after spreading, this level has to be reduced by 64 times as well. So there's a typo in this diagram. This level should be reduced by 64 times here. Okay? So try to correct for these mistakes yourself. So that the area of this should be the same as the area of this, because they have the same power. Okay? So let's say user 1 is assigned with one spreading sequence, and then the other users is assigned to spread using other spreading sequence, and you may have background noise as well. So they all share the same time, same frequency, so they mix up together. And then this is the base station receiver. At the input of this base station receiver, what you have received would be the blue part, which is the good term, right? The broken pieces from the reference user number 1. And then this yellow part will be the broken pieces from the other users, and then this gray part will be the background noise. Is that okay? So they coexist at the same time and same frequency. So that's why you have all these bad terms overlapping with the good term. Okay? So that's the input of your receiver. Now imagine you are the receiver. When you have this situation, what can you do about this? Is there any opportunity for you to clean up the bad terms from the good terms? In your undergraduate, if you study EE or related subjects, disciplines, you learn about filtering, right? You learn about digital filter, digital signal processing. Well, basically, digital signal processing is about filtering, right? So is there any opportunity for filtering? The purpose of filtering is to allow some good terms to pass through and block some bad terms from passing through, right? So do you see any opportunity of filtering? No, right? Because the good terms and the bad terms, they occupy the same spectrum, right? In order for you to have opportunity for filtering, the good term and the bad term must be separable in some domain, right? They should be separable in the frequency domain or time domain or some other domain, right? So, but now obviously, all these good terms and the bad terms, they are not separable in time, they are not separable in frequency. So you don't see any obvious opportunity for cleaning up the signal, right? Now, if you do not clean up the signal, and can you just treat the interference as noise and just go ahead and demodulate? Now, if you do that, then you have to worry about signal to noise plus interference ratio, right? SINR. The SINR, the numerator is the power of the good term. Now, these are power spectral density, so area gives you power, right? So power of the good term is the area of the blue part, right? So this is, let's say, 1 unit. And then the power of the bad term, interference plus noise. The interference terms are those yellow part. You can see that this yellow part in this example is like 3 units, right? Plus the noise maybe 0.5 unit. So it's around 3.5 units in the denominator. So that means this signal to noise plus interference ratio is even less than 1. So in terms of dB, it's less than 0 dB. Okay? So when you have a less than 0 dB SINR, even binary modulation cannot successfully demodulate. So you basically will have very bad performance if you just treat the interference as noise and go ahead with demodulation. Is that okay? So now that's the dilemma here you are facing, right? So if you don't have any other knowledge, then you cannot do anything about this, right? But let's say you are the intended receiver. Once again, intended receiver means you know the spreading sequence for the blue user. You also know the timing, let's say. So you are the intended receiver. So what can you do is, this interference or this signal term, they are not arbitrary signal, they are not random, they have some structures. The structure is the spreading structure, right? And if you know about these 2 things, being an intended receiver, what you can do is to do despreading, right? Now, if you do despreading using the blue key, okay, then because you know about these 2 things, so the blue part will be successfully reconstructed, successfully despread, right? For the other broken pieces transmitted by the other users, you are like despreading with the wrong key. So they remain as broken pieces after despreading. Is that okay? So after despreading, you selectively rebuild the good term, and then the other bad terms remains unchanged, remains as broken pieces. Okay? Now this is the picture of the spectrum, the situation of the spectrum after despreading. So let me ask you again, do you see any opportunity of cleaning up the good term and rejecting the bad terms? Now you see some opportunities, right? Because the good term and the bad term are partially separable in frequency, right? So what you can do is just a simple bandpass filter. So if you look at this spectrum after spreading, the good term becomes this guy. This is a good term. And then the bad terms are something like this. These are the bad terms, right? This is 64 times than the bandwidth of this good term, right? Why 64 times? Because I'm assuming I chop a symbol into 64 broken pieces at the transmitter, okay? So now, what you can do is, to clean up the good term from the bad terms is, okay, I can do bandpass filter like this. Now, after bandpass filtering, what do I have? After bandpass filtering, I will have the good term and some bad terms, right? So, after filtering, I have rejected a lot of the bad terms. There are still some residual bad terms remaining, but this power of this bad term, the power of the interference, the effective interference power is given by what? Remember, area gives you the power, right? So this is one part. This is 64 parts, right? So I have eliminated 63 out of 64 parts. So this guy is only 1/64 times of the actual interference power. Is that okay? So in other words, I have this magical discount factor. So this is like a discount factor I can enjoy, I can apply to the interference. By spreading and despreading, I am entitled to this discount factor. So although the actual interference power is this much, I don't need to worry about the entire interference power. I just need to worry about 1/64 times of that actual interference power, because that will be the effective interference power. That will still affect me after despreading. Is that okay? This is the reward I get by transmitting higher bandwidth. I chop a symbol into 64 pieces. The price I have to pay is I need to pay 64 times higher bandwidth cost. And the reward I get is I get this interference suppression factor, 1/64 times. Is that okay? So this is from a frequency domain, top level intuitive explanation, why spreading and despreading give you this interference protection. Okay? Because with despreading, you selectively reconstruct the good term and you do not change the bad terms. And that reveals an opportunity for filtering. Okay? So, and that's why you can get the interference suppression. Okay? And that's, so now let's look at this picture again in a more subtle way from the time domain equation. Okay? So this is the received broken pieces from the base station at the base station receiver input, which consists of the sum of all the broken pieces transmitted by the KF user plus the noise, right? So this signal corresponds to this input. It's just this is a frequency domain picture of this YT. This is the time domain equation for this YT. Is that okay? So, and now suppose I am interested in the KF user. So let's say this reference user is a KF user. The blue term is the KF user. And suppose I am the intended receiver. So that means I know the right code and I know the right despreading timing. So what I will have to do is I'll try to do despreading. Okay? So if I try to write down the equation, so this WKT is given by the despreading. What is despreading? I take these received broken pieces. I despread with the right key with the right time, okay? And I take the symbol average. That would be the despreading output. So this WKT corresponds to this picture, okay? So this is after despreading. Now, since I know the right key and the right timing, so if I try to substitute this broken piece, this mixture of broken pieces into this despreading equation, I will be able to split this into three terms. This is a good term, because SKT, CKT times CKT give you C squared KT. C squared KT becomes 1, right? So I get back SKT. And then these are the other terms. So I will get this SKT, the good term, plus the other terms. These are like the yellow interference, okay? Here, the yellow interference from the Jave user. And then take the simple average, and then noise. Okay, so it's split into these 3 terms. Now this is good because it contains the data for the reference user, user K. This is bad because it doesn't contain the data for the reference user. These are the data from the other users, right? And these are noise, of course, they are bad, right? So this term is an interference from the other users. So this is also called multi-user interference, because these are the interference contributed by the other users. Okay? In the classroom analogy, I'm the base station. This is like you guys start transmitting your data simultaneously. Okay? Overlap in time, overlap in frequency. Okay? Suppose I only want to listen to you. So what you transmit is a good term. So if I know about your language, I will be able to despread your broken pieces. So I reconstruct your data. But for the others who are speaking other languages, so they remain as broken pieces. So these terms are contributed by other users. So that's why it's called multi-user interference. And that's the reason I explained why in a commercial system, in a licensed spectrum environment, we still need to worry about interference. That's one example. This is coming from the other users. Okay? And this is noise. Okay? So now the thing is, now based on this time domain equation, now what I wanted to say is, now we have the freedom in the spreading and despreading process. We have the freedom to design what are the spreading sequence assigned to the K user. So that means we have the freedom to design what is C1T, C2T. These are something we can design. Okay? So what if, and we understand, and this term, by the way, this term is called cross-correlation. Again, correlation. We'll talk about this correlation concept a while ago. So correlation gives you a number to measure the similarity between 2 random numbers. Okay, 2 random guys. You try to compare how similar they are, right? So you can compute the correlation. And now this is to compare the similarity between the J spreading sequence and the K spreading sequence. Okay, so this is called cross correlation. Now, because we have the freedom to design the spreading sequence, so we can take 2 extreme approach. Okay, so let's say, so there are 2 versions of CDMA. One is called deterministic CDMA. The other is called random CDMA, which depends on how we design these spreading sequences. So let's look at deterministic CDMA first. So with deterministic CDMA, if we so the goal is, since this is a bad terms, and we can control this bad term by designing an appropriate sequence. So what if we design a sequence such that they are orthogonal? Orthogonal means the cross correlation. Let me give a notation. This is called RJK, 0, and the delay offset of 0. Okay, so that means if I design a sequence such that the cross correlation at 0 offset is 0, then that means this term is 0. If this term is 0, that means the entire multi-user interference term is gone. Okay. Now let me give you some example. It can be done. Suppose with a spreading factor of 4, if my spreading sequence, my first spreading sequence can be like this: +1, +1, -1, -1. Okay, so one symbol have 4 chips, right? So spreading factor of 4. My second spreading sequence can be like this, +1, -1, +1, -1. Is that okay? Now, if you try to compute this cross correlation means on every chip, you multiply these two together. That gives you plus, right? You multiply these two together, give you minus. Multiply these two together, give you minus. Multiply these two together, give you plus. And then you take the average here. The average gives you 0. Is that okay? So this is one example of so-called orthogonal sequence. Now you can design the sequence, and if you design the sequence in such a way that they are orthogonal, so that means if you can do this, then the multi-user interference term is gone. That means after despreading, you don't have to worry about this interference term. You only have to worry about the noise. So this would be nice, right? So that's the motivation of designing the sequence like this. So if you design a sequence like this, this is called deterministic CDMA. Now, however, the issue is this is a very strict requirement. Very strict requirement in the sense that you don't have too many such sequences that are mutually orthogonal. Okay? In fact, the number of orthogonal sequences is simply given by the spreading factor. That means if I chop a modulation symbol into 64 pieces, I can at most find 64 orthogonal sequences. Okay? Why is that? Because you can think of a sequence as a vector on a 64-dimension space. The fact that each of these vectors must be orthogonal to each other, and at the same time, the space is 64-dimension. So how many orthogonal vectors exist in a 64-dimensional space? Only 64, right? So that's because of this constraint. So number of orthogonal sequences you can find is given by the spreading factor. Because the spreading factor determines the dimension of your spreading sequence space. Okay? So that means now I'm going to assign one sequence to one user, right? In this game, CDMA. So if I can only find 64 orthogonal sequences, that means I can only support 64 users, right? Okay? So in other words, the capacity is limited. The number of users you can support is limited by the number of orthogonal sequences you can find, which is in terms limited by the spreading factor. Okay? It's limited. Moreover, in terms of implementation, there is also another constraint. This benefit of this orthogonal sequence, that means the cross correlation being 0, can only be realized with synchronous despreading. So you need synchronous despreading. What do we mean by this? When you despread the broken pieces, you need to make sure that the first chip of all the other spreading sequence align with the first chip of your despreading sequence. That's called synchronous despreading. The reason is because by careful designing this sequence, you can only guarantee that this sequence gives you 0 cross correlation at a 0 offset. For the same design, if you shift it by one chip, then the cross correlation will not be 0 anymore. Okay? So because of that, in order to enjoy this benefit, you need to make sure that when you despread, this term appears as cross correlation with 0 offset. Okay? That means the first chip of the despreading sequence should be time aligned with the first chip of the other spreading sequence. Now, this is a huge constraint in implementation. Usually, in downlink, it's easier to maintain this synchronous despreading, but not in uplink. So that's why in practice, in the next chapter, we will talk about the details. Most of the CDMA system, in the downlink direction, they are adopting deterministic CDMA, but not in the uplink direction. There's one exception. In 3G, China proposed a standard called TDS CDMA. So TDS CDMA is trying to do synchronous despreading, that is the deterministic CDMA, on the uplink as well. But that turns out to be not very effective for some reason I'm going to explain. Now, why do I say this is more favorable to downlink than uplink? So let's try to explain the synchronous despreading. Let me erase all this. Let's first consider the downlink situation. So let's say this is the base station transmitter. This is time. So let's say the base station is supporting 2 users, okay, at different locations. So the picture is this is base station transmitter. This is user 1. Maybe this is user 2. Okay. Now they are using CDMA. So base station send the data to user 1 using one spreading code. That is S1T, C1T. So they send broken pieces to this UE1 this way. At the same time, base station also send the data to UE2 like this on the spreading sequence of C2. And don't forget this is CDMA. That means these broken pieces transmit at the same time, sharing the same spectrum. Okay, so they overlap in time and frequency. So the base station transmit. So how do you maintain synchronous despreading? So synchronous despreading, suppose C1T and C2T are orthogonal codes, carefully designed orthogonal code sequence. Okay, so that means they give 0 cross correlation. That means C1T, C2T, take the average, is 0. Okay? So in order to maintain this benefit, when you despread at the user, you want to make use of this benefit to eliminate the multi-user interference. Let's say the transmitter just need to make sure that the transmission timing of these 2 broken pieces are aligned. So let's say, what do I mean by this? Let's say this is the first chip of the broken pieces to user 1. And then this is the, let me use a different color. This is the first chip of the broken pieces to the second user. Okay? So at the base station transmitter, they just need to make sure that these 2 broken pieces to the 2 users, they leave the transmitter at the same time. That means the first chip of the user 1 sequences leave the transmitter along with the first chip of the broken pieces for the second user. Okay, so they're time aligned. They leave the transmitter at t equal to 0. Okay? Now, when this happens, let's look at the timing for UE1. The timing for UE1 will be, this is the receiver 1. This is time. So you will have some propagation delay, right? So this will be the timing. So let's say S1T minus tau 1, C1T minus tau 1. So these are broken pieces for UE1. But along with it, the broken pieces for UE2 will be like this. This is S2T minus tau 1, C2T minus tau 1. Is that okay? So that is the timing at the input of the receiver 1. Now you are the intended receiver. That means you know the key, C1T. You also know the despreading timing. The despreading timing will be this timing, right? Then you just go ahead with the despreading. So despreading means you align yourself with a despreading sequence, like this, so that the first chip of the despreading sequence align with the first chip of the broken pieces that you receive. Okay? And now you do despreading. When you do despreading, this component will generate S1T minus tau 1, the complete symbol that you want. And then this back term, the interference term from this, for the second user, would appear as S2T minus tau 1, C2T minus tau 1, and then C1T minus tau 1 average. And this term is just the the cross correlation, right, with 0 offset. And this, by design, is 0. Is that okay? So because of that, after despreading at UE1, you will only get the good term, and the interference term for the second user will be gone due to this orthogonal sequence design, and due to the fact that you can maintain the synchronous despreading timing. Okay? I don't need to draw the picture for the UE2. It's the same, right? It's just this propagation delay will be different for UE2. Right? But it's the same idea. When you despread for the UE2, the despreading process is also in a synchronous manner. So you can see that in a downlink direction, from the base station, from one transmitter to multiple receiver, you want the receiving timing to be synchronized. You just need to make sure that the transmit timing is synchronized. And that's easy to achieve. You just need to, because it's all under your control at the transmitter. Is that okay? This is what we mean by synchronous despreading. Now, what about the uplink? From mobile as a transmitter, then base station becomes a receiver. This is called the uplink. In the uplink, if you try to apply deterministic CDMA, it's not going to be, you won't be able to enjoy this benefit of zero cross correlation because it's difficult to maintain synchronous despreading. So let's look at the uplink. Now, in the uplink, the UE becomes a transmitter. This is transmitter 1. Well, let's say in the transmitter 1, in the same process, you send the broken pieces like this, so that the first chip of your broken pieces is transmitted at t equal to 0. And then the second transmitter, you do the same. The second transmitter, you make sure that the broken pieces, the first chip of the broken pieces, are also transmitted on the same timing, like this. Okay? But the fact that UE1 and UE2 have different propagation delay to the base station receiver. So let's look at the timing at the base station receiver. So the broken pieces from user 1 will be received with this timing. This is S1 t minus tau 1. C1 t minus tau 1. Okay? And this is tau 1. But the received timing from the second user will be like this. This is tau 2. This is S2 t minus tau 2. C2 t minus tau 2. Can you see that? So the first chip of the broken pieces from the two users are not received at the same timing. In this way. Now, in this case, if you try to despread at the base station, let's say you are the intended receiver for the first user. So you know the first, you know the chip sequence, C1T. You also know the right despreading timing. This is the right despreading timing. So you go ahead and despread as usual. Right? So this is your local despreading chips. So you despread. If you despread, you know that this term, this component, will give you the good signal, right? We covered. But then, the bad terms, these blue terms from the second user, when you despread this is like despreading with the wrong timing, right? So what you have is this guy, C2 t minus tau 2, and then C1 t minus tau 1. And then you take the average of this. Now, what is this? This is cross-correlation with a non-zero offset, right? What you have designed is only guaranteeing, if you take the cross-correlation between two sequences with zero offset, you give you 0. But the same sequence will not be able to guarantee this cross-correlation with non-zero offset will give you 0 as well. And very likely, this is not 0. And that is called asynchronous despreading. Is that okay? So if you, after despreading, you don't get the benefit of having zero cross-correlation, that means you will still have the multi-user interference term. Then that defeats the purpose of deterministic CDMA, right? Okay, you carefully design the code sequence, but at the end you won't be able to enjoy this. Is that okay? So that's why in most CDMA systems, the uplink direction, they are not using random deterministic CDMA. Okay. Now I mentioned there's one exception, the China version for 3G, TDS CDMA. They try to adopt deterministic CDMA in the uplink as well. So how is it possible? Suppose you are the system engineer in China. So how do you make, for deterministic CDMA in the uplink, that means you need to make sure that the receive timing of these broken pieces from different users, they have to, no matter where they are, they need to arrive at the base station receiver at the same time, right? So how is it possible? What can you do to make sure that the receive timing of the broken pieces from different users, no matter where they are, they will arrive at the base station receiver at the same time? Now, you may find it difficult to understand in this context, but let me change this to an equivalent problem. Let's say next week, I require each one of you to arrive at this door at 7:15 sharp. Okay? You cannot arrive ahead of time and wait. Okay? You need to naturally arrive at the same time. If this is the requirement for each one of you, how can you accomplish this mission? What do you need to know first? Well, very easy, right? You need to know how long it takes you from your home to this door, right? Ahead of time. If it takes you 30 minutes to get to this door, then you should leave your home at 6:45, right? If it takes you 1 hour to leave to arrive at this door, then you should leave your home at 6:15, right? So each one of you, if you know your propagation delay, then you just arrive, you just transmit ahead of time, right? So that they arrive at the same timing. It's the same idea, right? So if each of the users know about the propagation delay, tau 1 and tau 2, what they need to do is, if you want them to arrive at the same timing, let's say you want them to arrive at t equal to 0 for the user 1 and user 2, like this. Then this guy just needs to transmit not at t equal to 0, but at t equal to minus tau 1, right? And this guy needs to transmit the first chip at the timing of t equal to minus tau 2. In this way, both will arrive at t equal to 0 at the same time, right? This is called timing advance. Okay? Using this timing advance mechanism, you will be able to maintain this synchronous despreading condition at the base station receiver for the uplink configuration as well, right? The critical requirement for this timing advance is you need to know tau 1 and tau 2, right? But how do you know tau 1 and tau 2? Are they constant? Are they something very constant that won't change over time? Obviously not, right? Like how long it takes you to get from your home to this door is also not constant, right? Depends on traffic condition, depends on a lot of factors, right? Same here. It depends on where is the mobile, right? The mobile are moving all around. So that means you need to have some mechanism to keep track of this tau 1 and tau 2 all the time. So how do you keep track of tau 1 and tau 2? The mobile has to send some preamble, some pilot sequence, or some beacon, so that the base station, by receiving this beacon, they will be able to feedback to the mobile what would be your tau 1, okay? And the mobile has to keep on sending this preamble all the time. So this preamble transmission will be an overhead, right? Okay? So, and moreover, when we say they need to arrive at the same time, what do we mean by arrive at the same time? There is an accuracy requirement, right? The precision required will be within a chip resolution. And a chip is of the order of microsecond. Okay? A chip duration in 3G is of the order of microsecond. So that means in order to achieve arriving at the same time up to the resolution of microsecond, you need to estimate this tau 1 and tau 2 also up to the resolution of microseconds, right? Otherwise, if you only have a rough estimate of tau 1 and tau 2, how can you guarantee they arrive at the same timing in the resolution of microsecond? That's not possible, right? So therefore, it consumes huge overhead to estimate tau 1 and tau 2 on each user to the resolution of microsecond. And then you need to keep track of that all the time. So it turns out that the benefit of this deterministic CDMA in the uplink cannot overcome the overhead, the huge overhead involved in maintaining this timing advanced loop. Okay? So that's why at the end it doesn't fly. You understand what I mean, right? The whole thing goes back to the requirement of synchronous despreading. Okay? And that's deterministic CDMA. Once again, you hope to design, by carefully design the spreading sequence assigned to each individual users, you hope to achieve this zero cross correlation. But this zero cross correlation condition can only be maintained under zero offset, zero timing offset. Okay? So therefore, for deterministic CDMA, the capacity is limited by the number of such PN codes or spreading codes you can find. Zero cross correlation is a very strict requirement, so you cannot find plenty of this. The number of codes you can find is just given by the spreading factor. Okay? So if you chop a symbol into 64 pieces, you can at most find such 64 such orthogonal spreading sequence. And that means at best you can only support 64 users. Okay? But there is also another condition. You need to maintain synchronous despreading in order to enjoy this benefit. So this is usually implemented in the downlink direction. Okay? Any questions? Okay, so that's why we say that this is code limited. Okay, so this is a good time for a 15-minute break, and after that we'll talk about the other version, random CDMA. Okay, so let's have a 15-minute break. testing. Okay, let's continue. So we talk about deterministic CDMA. The limitation is, number one, the number of Coke sequences that have zero cross-correlation is very few. The maximum number is only given by the spreading factor. And number two, you need to maintain synchronous spreading in order to enjoy the benefit. So it's very restrictive. Okay. So what if we relax the requirement a little bit? Instead of requiring them to have zero cross-correlation, what about we just require them to have a small cross-correlation? I will define what we mean by small. Okay? So instead of requiring them to be zero, we just require them to be small. Now it turns out that if we require these to be small, there are plenty of Cokes that can satisfy this small cross-correlation. And the cross-correlation can be small for all offset as well. Okay? So that means if I relax this requirement, number one, I suddenly can find plenty of Cokes. Number two, the condition to enjoy this benefit is no longer synchronously spreading, because this small condition can be maintained for any timing offset as well. You don't need to make sure the timing offset is zero. So that means this small cross-correlation benefit can be enjoyed even for asynchronously spreading. Okay? So that means this will be ideal for the uplink situation. You don't need to have this sophisticated timing advanced loop to make sure that the first trip of all the sequences arrive at the receiver at the same time. You don't need that. Even if they arrive at different time, you will be able to enjoy this small cross-correlation. Okay, so that's the two benefits. Number one, plenty of Cokes. Okay, number two, you can support asynchronously spreading. Okay, so these are the, and if we do it this way, this is called random CDMA. Now, just to clarify this concept a little bit. Now, let's say with this relaxed condition, I can find suddenly 2,000 spreading sequence that can have this kind of behavior. Now, I'm going to assign one spreading sequence to one user as always, right? So does that mean I can support 2,000 users? Understand my question? Now, previously in deterministic CDMA, I said that you only can find 64 such orthogonal sequence. And I'm going to assign one spreading sequence to one user. So that means I can only support at most 64 users, right? Now, with this relaxed condition, I'm able to find 2,000 spreading sequence. And I'm going to assign one sequence to one user, right? Does that mean I can now support 2,000 users? Understand the logic? Obviously, your intuition would not be possible, right? But why? What's wrong with this logic? I'm going to assign one spreading Coke to one user, and now I can have 2,000 spreading Cokes that have this small cross-correlation behavior. So why I couldn't support 2,000 users? Because in this case, the bottleneck is not the number of Cokes. The bottleneck is the interference. Because of small cross-correlation, this term is no longer zero, right? So as you have more and more users exist in your network, this multi-user interference term due to this summation, it will build up, right? So at the end, your capacity limit will be determined by the maximum tolerable interference power by this term. So yes, you can have 2,000 Cokes, but at the end, the number of users is determined by the maximum tolerable interference power. Okay? So therefore, you cannot support 2,000 users with this. At the end, the system capacity in random CDMA is interference limited. Okay? This is in contrast with deterministic CDMA. Deterministic CDMA is Coke limited. So why in deterministic CDMA we don't need to worry about interference? Because in deterministic CDMA, this term is zero, right? When this term is zero, there is no interference. So the only limitation, the only bottleneck is how many cokes you can find, right? But in random CDMA, now is the other situation. The number of cokes you can find is plenty, but it doesn't mean you can support however many users you like, because now the interference term is not zero. And this interference power will build up as you accommodate more users. Okay? So your capacity in this case will be interference limited. It's limited by your maximum interference you can tolerate. Okay? Now, but the good thing is this asynchronous despreading is very convenient. So you will be able to enjoy this asynchronous despreading for any topology. So it can be applied in the downlink, and of course it can also be applied in the uplink. And as it turns out, most of the commercial system, downlink is using deterministic CDMA because topology-wise, it's easy to maintain synchronous despreading. But uplink is usually using random CDMA because for uplink topology, it's not that easy to maintain synchronous despreading. Okay? So I said that this is small. What do we mean by small? So in fact, you don't need to have very careful design on the spreading sequence, and it automatically will have this small cross-correlation behavior. So even if you arbitrarily, just casually, so suppose my spreading factor is 64. Okay? So every chip sequence will have 64 chips, right? So if, let's say, I flip a coin to determine the realization of each chip. So I flip one coin, this is plus. I flip another coin, this is plus. I flip the third coin, minus. Flip the fourth coin, plus, etc. I flip 64 coins. Then I will have one sequence, right? And this sequence is randomly generated. This is called random sequence. So I flip 64 coins, I can get one sequence. I flip another 64 coins, I get another sequence. I can generate the sequence this way, right? By keep on flipping coins. Okay? Now, so I don't have any design, any special design. I just randomly flip the coins. Now, with this kind of casual random codes, people can already show that this cross-correlation have this behavior. It will scale like 1 over square root spreading factor. So if your spreading factor is 64, this will scale like if you double the spreading factor, this cross-correlation will be reduced by 1 over square root 2. This is the scaling law. Okay? Now it turns out that by randomly flipping the coins to design the sequence, you will have this scaling law. If you carefully design the chip sequence, the difference is this coefficient behind this scaling law will be smaller. But the scaling law remains to be unchanged. Okay? So this is pretty fundamental. So now this term appears in the multi-user interference term as an amplitude. So if you evaluate the power, you have to square this term. When you square this term, the power becomes 1 over spreading factor. So this is consistent with the frequency domain picture. Remember in the frequency domain picture, I explained you get the discount factor to the interference of 1 over 64, right? That 1 over 64 is the discount to interference power. And now this is 1 over square root spreading factor to the amplitude. Okay, so if you square this, you get the same discount factor of 1 over 64 to the interference power as well. Okay, so this is consistent with the frequency domain picture. Okay, and that's what we mean by small cross-correlation. Any questions? So this is random CDMA. So random CDMA, once again, now, this is the tricky part. With deterministic CDMA, because this interference term is 0, so the channel partitioned this way is still orthogonal channels. What you transmit for user 1 will not interfere with user 2, right? So it's similar to TDMA or FDMA, orthogonal channels. But for random CDMA, the cross-correlation term is not 0, but small. So that means what you transmit from the jth user will affect the kth user. That means channel partitioned this way is no longer orthogonal. So for random CDMA, we have non-orthogonal channels. Now these non-orthogonal channels will have some implication to the operators, as I will explain later. Okay? And as I explained, this is interference limited, but since it can support asynchronous despreading, so it can be used in the reverse link without any overhead. Okay? Now, to further illustrate, so I didn't elaborate here, but to further illustrate, what do we mean by interference limited? let's try to calculate the capacity of random CDMA. Well, to help the visualization, let's imagine this axis is the power in dB. Okay? And now let's say we have a base station, and then we have a user. Okay? Talking to the base station in an uplink direction. And let's further assume no matter where is the UE, no matter where is the mobile user, the receive power is always received at a power level of S. Okay? For some reason, which I'm going to explain. Now, in the system, in the initial state, let's say the system only have one user. So only one of you are talking to me. Okay, I'm the base station. So in this case, let me draw two levels. This is the noise power in dB, in dBm. This is the receive power in dBm as well. Okay, receive power for user 1. So what is this gap? This gap is the signal to noise ratio, right? So this is the signal to noise ratio for user 1. So this is pretty large. So user 1 is very happy. The physical layer, the error probability is pretty low, okay, for user 1 in this case, because there is no interference. Okay? Now suppose a second user comes in. So he's using CDMA, random CDMA. So it's sending the signal to the broken pieces to the base station. Again, receive at the same power S. Now let's consider user 1 as the reference user. Now when the second user comes in, the second user will be an interference to user 1, right? So the interference power is also given by this level S, right? That's the actual interference contributed by the second user. Now, however, because you are using spreading and despreading, and random CDMA, right? You got a discount factor of 1/64 towards the interference power, right? So the effective interference power that will affect user 1 after spreading and despreading is not the entire S. The actual interference power that will affect user 1 is, let me call this delta. So this delta is simply given by S divided by 64. That's the interference suppression due to spreading and despreading. Is that okay? So this is the effective interference power contributed by the second user. Is that okay? Now in this case, the reference user will have to enjoy this SINR. This is the signal to noise plus interference ratio, this gap. Okay? And this gap is still okay. Now, when the third user comes for the same logic, the third user will contribute an actual interference power of S, right? But due to spreading and despreading, the actual interference power that will affect user 1 will be, again, the delta. So as every time when one user comes in, you contribute an additional delta, right? So every new user comes into the picture, you will increase the interference flow by a little bit of delta due to the spreading and despreading protection. So at the end, what determines your maximum number of users? Let's say this is the maximum tolerable interference, because this defines a gap that, let's say this is the gamma. This defines a gap that the physical layer of user 1 will need to operate at SINR above this gamma, because if you exceed this level, the error probability will be worse than the target. Okay? So this is the maximum tolerable interference. And this maximum tolerable interference determines how many delta you can accommodate. Is that okay? So that's the idea. Now if I turn this intuition into equations, it's actually given by this. Suppose you have k users in the system. And we consider reference user number 1 as the reference user. So if we look at the SINR for user 1, the numerator is given by the power of the received, the good term, right, which is S. The denominator is the power of all these bad terms, right, which is the noise plus the interference, right? So with k users in the CDMA system, how many interferers to user 1? K minus 1, right? The other users are interferers, right? So you have k minus 1, each interference will contribute a power of S, right? So this term is the actual interference power, right, to user 1. But due to spreading and despreading, you don't need to worry about this entire interference power. You just need to worry about 1/64 part of this. Is that okay? Now this is the overall SINR. That is this gap when you have K users in the system. Now of course, the SINR for user 1 will have a requirement. This guy needs to be larger than a certain requirement. This requirement is determined by what? By the physical layer design. For example, if this is an error probability, this is the SINR for user 1, you have a curve like this, right? So suppose your application requires this error probability of 10 to the power minus 3, okay? And this will in turn require a certain requirement here. Let's say this requirement is 7 dB. And that means you need to make sure that this SINR for the user 1 has to be larger than or equal to 7 dB. Because if you exceed this, if you get below 7 dB, then the error probability will be higher than this target. And then you are not meeting the demand of the application. Okay? So this equation will give you the constraint on the number of users you can support. Now let's try to simplify this equation a little bit. First of all, assuming that the power that you receive is very large. Okay? So this is we take the limit when the power is very large. So when the power is very large, the denominator, you can pretty much ignore the noise term, right? So this is interference limited. When you ignore the noise term, the numerator and denominator get cancelled, right? So that means the performance cannot be improved by increasing power. So this is once again the standard behavior of interference limited system. And suppose we have a sufficiently large number of users. So k minus 1 is approximated by k to simplify the equation. So at the end, the number of users you can support is simply less than equal to the spreading factor divided by the required SINR. It's a very simple formula. Is that okay? So this is coming from this logic. As you increase more users into the random CDMA system, the interference level will build up. So the capacity limit will be when you exceed the maximum tolerable interference. And that would be the situation when you hit the capacity limit. And this is the equation to express this intuition. Okay? So that means there are only two ways you can increase the number of users, the so-called capacity. Number one is increase the spreading factor. I'm using an example. I chop a symbol into 64 pieces. So my spreading factor is 64, right? If you want to double the capacity, I need to chop the symbol into 128 pieces, for example. Okay, then I will get double the capacity. But I need to pay the price. What's the price I need to pay? The bandwidth cost needs to be expanded by 128 times instead of 64 times. So I need to double the bandwidth cost. So that is a fair trade-off, right? That's one way I can increase the capacity. The second way I can increase the capacity is to reduce my requirement on the physical layer. So if, let's say, my physical layer is more robust, so instead of requiring 7 dB, I just require 5 dB. Okay? Then I get a smaller denominator. That means I can tolerate higher interference level because of my robust physical layer. And that in turn translates to higher capacity. Is that okay? Remember when we talk about flat fading, we say that the penalty of error probability curve is like this, right? So the error probability curve becomes flatter. So I explained at that time, from coverage angle, you may be able to live with this by increasing the transmission power. But from capacity angle, let's say if you are operating on using random CDMA, this extra penalty cannot be overcome by higher transmission power. So if you have flat fading and you do not deal with this, then that means your gamma requirement will be higher, maybe 10 dB higher. And if this 10 dB higher is not, you don't use any diversity technique, then this extra 10 dB will end up having capacity penalty because your denominator now is bigger. That means in this picture, your maximum tolerable interference will be lower. Okay, so you can accommodate, you have less room to accommodate users. So this is the the mechanism. Is that okay? So this is the so-called interference-limited situation for random CDMA. So in fact, random CDMA, due to this interference limitation, so for in the next chapter, you will see that in practice, IS95, in the downlink, they have a spreading factor of 64. So they can support at most 64 orthogonal channels. But in the uplink, they use random CDMA, and turns out that the uplink capacity is only around 16 to 15 users. It's far below 64. Okay, so and that's the reason. The reason is because you have interference between users. Okay, so that's random CDMA. Now here I make one very important assumption. I am assuming that no matter where you are, the receive power is the same. That means if I'm the base station receiver, you guys are talking to me using random CDMA, no matter where you are, your receive power at the input of my ears will be the same. Okay. Now if you deviate from this, let's say you have someone close to me, and that guy is crazy, just shouting at me. Okay. So the receive power from that user will be very high. So he himself will be very happy, right? Because he has a higher good term power, right? But this single user, single misbehaving user, may contribute a much bigger delta than the other users. Now, if that's the case, just one or two such crazy users will eat up all the capacity, because the capacity is measured by this margin. Is that okay? So, and that's because of that, for any random CDMA system, maintaining this condition is very critical. So that problem I just described is called the near-far problem. If there's a nearby user transmitting like crazy, shouting at me, this single misbehaving user can eat up all the capacity margin, and there's no more room for other users. And so for a random CDMA with near-far problem, the random CDMA is more or less useless. Okay? So to deal with this problem, you need a very sophisticated power control scheme. And that will be also the subject in the next chapter. So if you look at any CDMA system commercially, you need to understand a CDMA system. You need to first understand the power control mechanism. The power control is not for saving your battery power. It's for much more fundamental purpose. It's to maintain a reasonable capacity in random CDMA in the uplink. In other words, without this sophisticated power control, the random CDMA would be useless. Okay? Now, before I close this session, let me illustrate. So far I have illustrated spread spectrum using random CDMA or deterministic CDMA, how they overcome this multi-user interference, which is one source of interference in a commercial system, right? I mentioned the other source of interference is the intersymbol interference due to frequency selective fading channel, right? And that will happen even if there's a single user only. Okay, so let's look at how CDMA, how spreading and speed spreading help with this ISI problem that we talked about last week. Now, this is done using something called rate receiver. So let me explain this, the model. So now let's say for simplicity, let's only consider one user. Okay, one user on a two-path channel. So let's say the channel has a memory of 2. Okay, so when you say the letter A, you will hear as A, 2 distinct symbols for easy discussions. So this is the base station transmitter. Let's consider downlink direction. So the base station transmitter will send these broken pieces given by the data spread with this spreading sequence. Okay, so this is the first chip of the broken pieces sent by the base station, like this. So these broken pieces reach the receiver through two resolvable paths. This is the first resolvable path with a delay D1. This is the second resolvable path with delay D2. And at the end, the receiver will receive a mixture of these two. Is that okay? So in terms of the equation, let's also consider fading. In terms of equation, the received signal, the broken pieces received at the receiver consists of alpha 1, ST minus D1, CT minus D1. That's coming from the first resolvable path, plus alpha 2, ST minus D2, CT minus D2. This is coming from the second resolvable path, and then the noise. Is that okay? Now, at the receiver, let's say you are the intended receiver, right? So you want to go through desthreading. And as we talk about, successful desthreading requires two conditions, right? What are the two conditions for successful desthreading? Number one, you need to know the threading sequence, right? So suppose the receiver knows about the sequence. Number two, you need to know about the desthreading timing, right? So now look at this picture. What are the possible desthreading timing? There are two possible desthreading timing, right? The first timing is you can align with D1, right? You can align your local spreading sequence, CT minus D1 here. Align with the first resolvable path. If we dissolve, so let's try this. Let's try the first desthreading timing. This is given by the broken pieces that you have received, and then you desthread with the known spreading sequence aligned with this timing D1. Okay? Now if you do this, you substitute into this equation, you get three terms. The first term is a good term, alpha 1 as t minus d1, and then c squared t minus d1, which is a 1, right? Then the second term, due to the second resolvable path, will be alpha 2 as t minus d2, c t minus d2, and c t minus d1. And then take the average and noise. It will be something like this, right? So this becomes a good term because it contains the data. Recover data, successfully desthreaded contribution. But this good term is now mixed with these bad terms. So this is a bad term. What is this? This is the interference contributed by the second path, right? So this is the intersymbol interference. Is that okay? So that's the ISI effect that we talked about last week. Remember last week we say that if you say a letter A, you hear your voice as A, right? Then the echoes of your previously transmitted symbol will interfere with your current transmitted symbol. So this is the echoes of your previously transmitted symbols. And then this is the noise, of course, it's bad. Okay? Now, again, as I said, we can have the freedom to design the spreading sequence, right? So now let's say we design the spreading sequence in a random way, just like the random CDMA. If my spreading factor is 64, I flip 64 coins to determine one realization of the spreading sequence. Okay? So if I do random code, this term is now called autocorrelation. Again, correlation. Correlation is the measure of similarity between two random numbers, right? So now this is measuring the similarity between the spreading sequence and the delayed version of itself. Okay? Now it turns out that, again, it can be shown that with this random spreading sequence design, this autocorrelation will be small. And how small is small? This is again of the order of 1 over spreading factor in amplitude. That means if I double the spreading factor, this autocorrelation value will be reduced by 1 over square root 2. Is that okay? In amplitude. That means if you look at the power, it will be reduced by 2 in power. Because power, you have to square this term. Is that okay? So now with this, that means, yes, you still have ISI. But the ISI power is mitigated by this autocorrelation factor. So this is like the discount factor we talk about, right? If I chop a symbol into 64 pieces, the interference power that will affect you, the effective interference power, will be 1 over 64 times of the actual interference power, right? So here is another example. If you look at the ISI power, so from this you can see that the effective interference power is equal to the actual interference power times 1 over 64. Right? Also have this behavior. So it seems like with CDMA systems, you are entitled to this discount factor towards any interference you come across. We demonstrated this through random CDMA. With random CDMA, you can have this discount factor of 1 over 64 to multi-user interference. And now this is a second example. You also have 1 over 64 discount factor towards the ISI power as well. Okay? Now with this, what's the implication? So if I try to plot the error probability versus SNR. So this is the curve over frequency selective fading, right? You have this irreducible error floor, right? Suppose you don't have any spreading, no spreading. This is the curve you have to bear, right? So this is two-star problem. This is falling off slowly in the noise limited region. And then you have this irreducible error floor in the interference limited region, right? So now if you apply the same modulation and demodulation, let's say this is BPSK. If you just apply BPSK and spread spectrum, and then you try to demodulate based on this, the spreader output W1, then what would be the error probability curve? The error probability curve will be like this. This is BPSK with spread spectrum on W1. The irreducible error floor would be substantially reduced. Why? As we mentioned last time, this irreducible error floor is due to the saturated SINR, right? So the saturated SINR have this signal power as in the numerator, and then this interference power in the denominator. But now this interference power is mitigated by this factor, right? So you have 1/64 times in the denominator. So therefore, that means the saturated beta, if you remember my notation last time, the saturated SINR now is increased by 64 times. Is that okay? So when the saturated SINR increased by 64 times, that means the irreducible error floor is reduced. So this also provides a guideline on how large the spreading factor would be required. So suppose your application demands this error probability. So if you do not do spreading and despreading, your error floor is above your target. So you can never operate the physical layer to meet your target, right? So, with this, you can determine how many dB do you need to suppress the error floor. So from this, you just determine the appropriate spreading factor to bring you this discount factor with sufficient protection so that the error floor will be pushed below the target. As long as you push it below the target, that will be good enough because you don't need to worry about this error floor anymore. Is that okay? So this is the magic. By spreading and despreading, you are entitled to this discount factor given by the spreading factor. If this is not enough, if we need to push the error floor lower, then that means you need to use a larger spreading factor. Okay? But then this is not free. Using a larger spreading factor, that means you need a higher bandwidth expansion. So again, fair trade-off. So now this is an elaborated answer to the earlier question, why you want to do spreading and despreading, why you want to pay this extra bandwidth cost. The reward you get from this extra bandwidth cost is interference suppression. This 1/64 protection factor is coming from the price you pay for bandwidth expansion. Is that okay? Now, can we do better than this? Can we do better than this blue curve? Do you see any opportunity for doing a better job than this blue curve? Now here in this blue curve, you solve this irreducible error floor, right? There are 2 stars of trouble. You resolve 1 star. But you still have the other star here, which is falling off slowly, like flat fading, right? So can you have something that deal with this problem as well? Do you see any opportunity? Now, this is what can be achieved by doing this despreading with respect to the first timing, right? But as I said, this is just one of the possible despreading timing. What about if you despread with respect to the second timing? If you despread with respect to the second timing, let me write down the equation. W2 will be given by these broken pieces despread with the spreading sequence aligned to the second timing, like this, right? Now, if you do it this way, again, you will be split into 3 terms. The good term now becomes coming from the second path. Would be alpha 2 ST minus D2. This will be the good term, right? Coming from the second path. And then the ISI term will be coming from the first path. And then noise. You have something like this. Is that okay? So this is a good term coming from the second path. This is the ISI term coming from the first path. So now you can also demodulate based on this W2 output, right? Now if you demodulate based on this W2 output, you will get the same curve as the blue line. So this is demodulate based on W2 or W1. Because for the second despreading output, the despreader output, you also have the same discount factor. This factor will also, under random code design, also give you this order magnitude in the autocorrelation. So in terms of power, you will also have 1 over spreading factor discount in terms of the power of the ISI. Okay, so both the error flow will be suppressed by the same factor of 64 times if you demodulate based on W1 or W2. Is that okay? But once again, can we do better than this? You have W1. W1, the good term is affected by fading coefficient alpha 1, right? You have W2. W2, the good term is affected by fading coefficient alpha 2. Alpha 1 and alpha 2 are independent, right? Because they're coming from two resolvable paths. So what do we have? So we have two observations about the same information, and they suffer from independent fading. So what are they? W1 and W2 are naturally your diversity observations as well, right? So if you can make use of these diversity observations, you can achieve something like this. This is using W1 plus W2. Plus means diversity combining. Is that okay? So this is amazing. That means you can kill two birds with one stone. You can simultaneously address this slowly decreasing error probability curve, the one star problem here, another star problem here in irreducible error flow, right? This is the principle of weak receiver. You can despread with successful despreading. Now you have two choices on the despreading timing. If you despread along the first timing, you get one despreader output, which will be one observation. If you despread with respect to the second path timing, you get another observation. Okay, and these two observations suffer from independent fading, so they will naturally be your diversity observation. Is that okay? Now, if I'm again standing in the shoes of an architect, so your system guy gives you this equation, okay? So that's the output. Now, if you're the system architect, that will be your input. Now, how do you translate this into, let's say, an ASIC implementation, a chipset implementation? So, let me try to erase this. Maybe not, maybe here. So if I'm trying to map these equations into a chipset implementation, so the top level architecture will be like this. So you have these broken pieces as your input, right? So the first thing you need to do is you need to do despreading, right? So let's say you have a despreader doing this despreading operation. The output of the first despreader is giving you W1. The output of another despreader, number 2, is giving you W2. Is that okay? Now, this despreader, you need to tell the despreader where to despread. I mean the timing, despreading timing. So you need to control this to despread at D1, D2, like this. Okay? So that's the front end doing the despreading. After you do the despreading, what do you do next? You need to do diversity combining, right? Because W1 and W2 are your diversity observations. So using what we discussed previously, you need diversity combining. For example, selection combining, selection diversity, equal gain combining, or maximal ratio combining. These are the commonly used combining methods. Then you have the combined metric, right? Then you feed into demodulation afterwards. So that would be your entire receiver data path, right? And for this part, we have a name for this. This is called wake receiver. So why this is called a wake? So there's really a device called a wake. I'm not sure you know. So it's like this. Well, I hope you know what I'm drawing. So it's something used for gardening. It's a long handle with this kind of finger sticking out. If you don't know what I'm drawing, I guess you all know COG, right? So in COG, there's one character, Mr. Pig. And this is a weapon carried by this Mr. Pig. I hope this will help you to correlate. So this is called a wake. And why this is called wake receiver? Because you use a little bit of imagination. This is like the input. This is like the spreader. Each of this finger is like a despreader. So this is giving you W1, W2, W3, W4. Is that okay? So this architecture is called wake receiver. Now if you look at this, this example is just having 2 paths, right? So you have 2 despreader. Now if you have 4 paths, you can actually have 4 despreader, right? And the most complicated operation in this wake receiver is the despreading operation. Okay? So most of the complexity and power consumption comes from this despreader. So the overall complexity, as you can see, is the number of paths, right? Linear instead of exponential. So this is nice, right? Because as I told you before, brute force equalization and the receiver in general require exponential complexity. But now how comes this wake receiver only require linear complexity? Now the fundamental reason why you have this low complexity, you can think of that as a low complexity equalization. Okay? You suppress the interference by spreading and despreading. Okay? That's one form of equalization. The fundamental reason it works is not just because of this wake receiver architecture. The fundamental reason it works is because the transmitted signal has this built-in structure. The transmitter is sending you not just modulated symbols. They are sending you these broken pieces. These broken pieces are the built-in structure. And the wake receiver is just exploiting this broken pieces structure, the built-in structure, to achieve the low complexity interference suppression. Okay? So that's what I mean earlier on. If you want to have low complexity equalization, the transmitter can help a lot by sending something with some structure. And spectrum is one such example, that the transmitter, by sending this built-in structure, the broken pieces, the receiver can exploit this structure and achieve this low complexity interference suppression. Is that okay? Now, let me further elaborate on this architecture. Now, if I'm trying to build this as a synchronous logic, digital logic, so you know for digital logic you have clock, right? This is one clock. And then this is also another clock. Now this despreader, if I try to write down the equation, the processing equation, it's simply like this. I'm using 64 as my example spreading factor. So W1 is 1 over 64. R summation I from 1 to 64. RTI C TI. TI minus D. 1, for example. Okay, so this is what we mean by average, right? So we take a symbol level average. We take these broken pieces, multiply with the chip on a chip-by-chip basis, add up over 64 chips, and divide by 64. That would be the despreader output. Okay? Now, first of all, in terms of the complexity, in terms of the clock domain, so how many clock domain do we need for this entire receiver? for example, for this de-spreader, how often, you know the clock, right? So if you remember, for those with double E background, you should know that, for example, synchronous logic always have a clock, right? The clock is used to trigger the operation of the block. So usually on a rising clock edge, that will trigger the computation of the digital logic on every rising clock edge, okay? So for the de-spreader, how fast the clock will be needed for this de-spreader block? Is it a chip duration or symbol duration? How often do you need to wake up this guy to compute? Every symbol or every chip? You're going to compute this thing. How often do you need to compute? Of course, every chip, right? Because you need to sum up over the 64 chips, right? So you need to do the multiplication and accumulation every chip, right? If you try to turn this into a program, what do? For I equal to 1 to 64, this sum plus equal this thing, right? So if you think about C implementation, you will know what I mean. So this equation needs to be computed or triggered every chip duration. So this is a chip clock. What about this guy? Diversity combining. How often do you need to wake up this guy to compute? Suppose you do MLC, maximum ratio combining. How often do you need to compute? Chip level or symbol level? Of course, symbol level, right? Because this thing will be generated once every symbol, right? So you will only get a W after 64 chips. So you will only get one W after one symbol, right? So therefore, this is a symbol clock. Is that okay? So this entire data path will have two clock domains. Now, this is, if I'm using 64 chips as an example, this is this is 64 times faster than this symbol clock, right? So, and if you study CMOS logic, you know that the power consumption scale like the clock frequency to the cubic order. So if this is 64 times higher clock weight than this guy, so that means this guy burns 64 to the power cubic, more power than this guy's, right? So the complexity of this box will matter a lot because they are running at very high clock rate. This is just like if you buy a CPU, you try to overclock this, right? You may not always work if you overclock by too much. So there's an inherent, so if you need to design a digital logic that runs on a faster clock, the complexity that you can handle is very limited because the power consumption issue. So because this guy is running at 64 times higher clock rate, so the processing involved here will be very critical. So we need to examine further what is the combinatorial logic needed in the de-spreader. What do you need to compute? Now from this equation, what would be in this de-spreader? Do you need an adder? Do you need an adder? Of course you need an adder, right? Because there is a multiplication, there is summation here. You need an adder. Now, if you recall from your digital logic, a full adder is not too bad, right? A full adder is not too bad in terms of complexity. Do you need a multiplier? Do you need a multiplier? It seems you need a multiplier, right? Because you need to multiply. Now, but then recall from your digital logic, a multiplier is much worse than a full adder, right? To compute a multiplication, you need much more logic than a full adder. So if you need a multiplier here, which is running at 64 times higher clock rate, this is not going to be easy. But look at this equation closer. Do you need a multiplier? Do you need a multiplier? What are you multiplying? You're multiplying into this chip sequence, right? What is this chip sequence value? +1 or -1, right? You can only take two values, +1 and -1. If you are multiplying into +1 or -1 quantity, do you need a multiplier to do that? Of course not, right? If you multiply into +1, it's just the same number. If you multiply into -1, it's just a 2's complement, right? So you don't need a multiplier, fortunately, because of this chip sequence being +1 or -1. Although this is a multiplication, the implementation involves just some logic for two's complement computation. So because of that, the main complexity in the spreader is just an adder with some logic. Okay, so this is still manageable. So that's the good news in terms of the complexity consideration. Okay. Now, of course, do you need a divider? Divider is even worse than multiplication. Do you need a divider? You don't. Why not? If you have to divide by 64, what would be your implementation? You just need to shift the point, decimal points, right? This is the fixed point number. So divide by 64, which is 2 to the power 6. You just need to shift the decimal point by 6 places, right? So again, you don't need the divider to do this. All right, so this is the basic architecture for the rate receiver. Now, let me, there are still further discussions to do. Okay. I mentioned for successful despreading, we make an assumption, right? Successful despreading requires knowledge of the spreading sequence. So how would the receiver know about the spreading sequence? So in this example, the base station is sending you broken pieces. You are the receiver. How do you want to do successful despreading? The first condition is you need to know the spreading key, CT. How do you know the CT? Now, in the next chapter, we will see that in most different commercial system, there will be some signaling mechanism. The base station, for example, will tell you through some signaling channel that the spreading sequence is CT. Okay, so you know which spreading sequence the base station is sending you the broken pieces. Okay, through explicit signaling. That's one way. Now, successful despreading also demand you know the despreading timing, right? In this example, you need to know D1 and D2. How do you know D1 and D2? Can the base station tell you D1 and D2? Would the base station know what would be the despreading timing? No. Base station wouldn't even know what would be your despreading timing because that depends on where you are, right? So you have to estimate this despreading timing yourself. Okay, so next time we'll talk about the control path. This is the data path. So next time I will talk about the control path, how you actually determine D1 and D2. Okay, then that will complete the discussions. Okay, so in terms of time, let me stop at this point, and then I will talk about the other variations next time.